All right, so in Chapter 4, we start talking about network access. And in this chapter, we're going to start talking about device connectivity. We'll talk about the physical layer. We get all into the physical layer in this one. Physical layer is different, but you'll see that that doesn't really matter to a network because the data is still seen the same. I've said it again, I'll say it before. A 0 and a 1 is a 0 and 1, whether I'm sending it as a light signal or an electrical signal. The different layers of the physical or the principal standards will, they say build a UTP cable. I didn't bring the stuff, but if y'all want to experience that, I will bring some stuff and let y'all build an unshielded twisted pair cable.
Didn't I do that in 101?
Y'all should be doing that in 101. In fact, I got to get with Tom. I need y'all to build some long ones very specifically to hook those projectors up. So I'm going to give him the stuff. What room is that class in?
I'm just doing online.
Oh, okay.
I'm sure.
Yeah, online you won't, but his face-to-face classes, I've got 6,000 foot of wire sitting in a corner of one of those built rooms, so I'm going to let them build some cables. But I have the stuff if we get to it, and that's something y'all want to do. I'll tell you that is sort of the bane of existence to me as a net admin. I'm colorblind. I would rather do just about anything than build cables. My only saving grace is that I'm usually consistently wrong. And a consistently wrong cable, while not in standards, will work. As long as you get the same thing wrong on both ends, you're good to go. We'll talk about fiber optic and its advantages. Wireless. They've put a lot more emphasis on wireless now in Cisco, and I'm kind of glad because wireless is everywhere. I'll give y'all an example. I just changed phone companies. I went to Sprint because I got mad at Verizon. And why I got mad is silly, but the whole thing about limited data plans, they limited you to 1 gig of data, and even though I didn't get near it, it just made me mad that they were limiting you. But in truth, I stopped and thought about it, and in reality, I'm under a wireless network almost everywhere I go. I've got one in my office, there's one here, I've got one at home. Unless I'm actually in the car between the two buildings or something, I don't actually use the cellular network. I'm almost always on wireless. And I think y'all have noticed most businesses you go to now have got wireless. You can go to a restaurant and get on their wireless. Of the data link layer, a layer 2 frame, which we'll talk about. That's got MAC addressing in it. We'll talk about some of the protocols at that layer. We will talk about topologies, and that gets important. And remember back in Chapter 1 where I talked about physical and logical topologies. You got to be sure you know the differences in those. Then we'll talk about the media control methods on WANs and LANs and the functions of a data link frame. So here they're just giving you an example of a home router. This one I'm sure is a Cisco Linksys just from looking at it. Most of the new home versions of Linksys Cisco equipment have embedded wireless. Now, this is different from the old ones that actually had wireless antennas. And pluses and minuses, I'll be honest, I don't like the ones that have the built-in antennas. I like the antennas to be external so you can move the antennas away from the device if you want to. But most home people don't need that or not going to do that. So they've started making it where everything's just together. The Ethernet switch is the 4 ports. Then you've got an internet connection, which would be your WAN connection. Here they're showing to connect to a wired LAN. Basically, all you're doing is connecting a port to a computer. And in order to be able to do that, your computer's got to have what's called a NIC in it, or a network interface card. In fact, I'm betting your laptops have got more than one NIC in them. Mine's got 2. I've got wired on the side and wireless. And that's 2 separate network cards that do that. Make laptops without wired connections, but they're not very common. Probably the only one that I've seen that's a decently common computer without a wired connection built in is a MacBook Air. And the only reason it's not got a wired connection built into it is they made it so thin There's not room for one, but they ship it with a USB to wired adapter so you can plug it in. All right, so I went into this in the other chapter, but they want to explain again that data goes from a source to a destination, and it has to go all the way down the layers to the physical layer. Only the physical layer is actually connected to the physical layer of other devices. And then to get to where it needs to go, it's got to go all the way back up. And basically, whatever data is put on in one layer is taken off by that same layer on the other side. When I add layer 3 data on one side, I remove that layer 3 data at layer 3 on the other side. Here they want to show just a couple of examples of physical media. We've got at the top an electrical signal, like a copper cable. We've got light, fiber optics. I look for there to be a lot more fiber optic stuff in the future. And the reason for that is I think that we're nearing the end of speed that copper can handle. Gigabit copper is kind of pushing, but we now have 10 gigabit copper. And I believe you can only run that 25 meters before it pops out. It's too much on the cable. The cables aren't designed to handle that. And I think that if you look at buying stuff, like I don't know how much y'all have bought network stuff lately, but fiber optic stuff is coming down in price. And I think it's going to very soon reach a point where it's just almost as cheap as running unshielded twisted pair or shielded twisted pair to just run fiber. And then at the bottom we've got wireless. So physical layer standards, the ISO does a lot of those. The ISO 8877 are what are called the RJ connector standards. Two big examples, RJ11 and RJ45. RJ11 is what a phone uses. That's that standard 4-wire telephone connector that, well, I'd say most of you have at home, but I don't know how many of y'all actually have home phones anymore. In the old days, that would be a standard. A lot of people have done away with their phones, especially in a bigger city like this for wireless. RJ45, however, is what computers use, and that's the bigger connection that, runs into the back of all of these. The EIA-TIA sets up cabling standards, and a couple that are important are the 569 and the 560A, and these are the standards used for wiring closets. There's something that you're going to get into in 101 that we don't talk so much about in here, but you're going to see called structured cabling. This is that structured cabling approach. And the idea behind it is just organization. They'll tell you, like in a high-rise, put a wiring closet on every floor, put that room right above the floor below it, run fiber down the back plane of the whole building to connect the rooms, and then run copper from there out. So that's your vertical and your horizontal wiring. And they give standards basically on how to set all of that up. And the reason for that is not because it won't work if it's not standard, but if you do a standard or a company pushes their employees to do a standard, then when that person retires or quits or gets fired or whatever, somebody else can come in, and if it's following a standard, they should be able to take over the wiring and do whatever needs to be done. So some fundamental wiring and or physical layer principles. Copper cable, some examples, unshielded twisted pair or UTP, coaxial, network interface cards, ports, and interfaces. The encoding used, you'll hear this a lot, Manchester encoding, and that's how the data is actually converted into ones and zeros to be sent out on a piece of wire. And it's done by changes in the intensity of the electromagnetic field on that represents a 0 or 1, sort of a higher or a lower voltage. Fiber optic, you have single and multi-mode, and we'll talk about what those are later. But either one is going to use pulses of light. And a pulse is, a light is a 1, a no pulse is a 0. So timing is very important on fiber optic cables because they need to be synchronized with time to know to be looking for the presence or absence of a signal. And then wireless, is something that we've got radio waves, we've got access points. An access point is what everyone is going to connect to that's then going to hit the physical network. I don't know what chapter it's in. It's probably 7 or 8. It was in the old one, where we start talking about how wireless frames are very much the same as Ethernet frames with just extra data on them. And that becomes so important because so many people do mixed network right now. We're doing wireless on our laptops, but all these computers are physically connected. It still looks like one network, though, because the access point just pulls the wireless frame off and puts the packet on the network just like it is. So bandwidth is important to understand. And we've got some common ones. BPS is bits per second. A bit's a fundamental unit of bandwidth. Kilobit, megabit, gigabit, and terabit are just some different ones. Kilobit is 1,000. A megabit's 1,000,000. A gigabit is 1,000,000,000. What is the next one? Trillion? Something to know here, Cisco is rounding this off, and that's okay because when you talk about network, you'll say that you've got a 20 megabit pipe. Well, then that would roughly be 20 million bits. But in reality, make sure you remember, based on what test you're taking, that these numbers are rounded. Do y'all know why they're rounded? Computers really do, on a fundamental level.
Is it surrounded like by 8%?
It is. You're very much on track. And the reason for that is because computers are really binary. Even though we use these things and they're great, if you think about it, all it boils down to is a 0 or 1. And in binary, these numbers don't come out even. A binary kilobit is 1024, not 1,000. This is why if you buy a gigabit of memory for your computer or a gigabyte of memory, you'll have more than just if you rounded it to zeros. So here they're showing throughput, an 80 meg down and an 8 meg up. I guarantee you they're not in Shreveport. Here they're showing some of the different types of physical media. Fast Ethernet is the standard 100 megabit Ethernet. The management ports over here, this is where you would plug in a console cable to connect to a router. This router's got a couple of gigabit interfaces that would be used to connect to high-speed switches or other routers, and this one's got a couple of USB connectors on it. So some of the characteristics of copper, you'll see here they're showing a pure digital signal, and then they're showing one with some interference. And interference is important because that's something that happens a lot with copper. A number one problem are these fluorescent lights. Most buildings are wired with this, what are called drop ceilings. That's what we have in here, where if we took one of these off, there's space up there that's got all the wires in it. Well, you have to be careful with unshielded twisted pair and try real hard not to go over these lights, because these lights will produce a lot of electromagnetic interference when they're on. And it's really hard in diagnosing a network problem if it's a room that's not very used. Say the network works up here, but it doesn't work between 5 and 6 and you can't figure it out. Well, then you finally find out an unused classroom only has class from 5 to 6. So that light's not on except for that time. Unshielded twisted pair is still used so much, though, as it's cheap. Compared to all the other media, it's a whole lot cheaper right now. Here are their examples of copper. You've got coax at the bottom and then UTP and STP. And the difference is the shielding. STP has shielded pairs of cable in it, but it's more expensive because of that shielding. Here they're showing just an example of UTP. The wires are twisted together in sets of 4, or in sets of 2. There are 4 sets of twisted wires. And the reason for that, I assume the slides get into it later, but it's to eliminate something called crosstalk. Crosstalk is where signal from one wire will bleed onto signal from another wire. And the twisting keeps crosstalk from happening as bad on the different sets of wires. On a shielded twisted pair, and you see it's just got a full shield, and then each of the sets of wires have their own shield around them. That makes this cable where it can run longer, it can run faster, but it's also more expensive. And here's a standard piece of coax. Coax has got an outer jacket and then a braided copper shielding, some plastic, and then a copper conductor in the middle. And there are a couple of different types of coaxial connectors. N-type, unless you're doing something with radio, you're never going to see. But B and C and F-type are still pretty common. F-type is what most of you probably have at home if you've got cable internet or cable TV. B and C stands for British Naval Connector. And I have no idea why. I looked it up one time, but I don't remember what it told me. But the B and C connector is made to be quicker than an F-type connector, and it was used a lot in networks where you're actually connecting a network over coax versus like cable that's encoding it before it goes over coax.
We used to use it on the aircraft I worked on. They connect to it.
BNC?
Yeah, you can plug it really quick.
Yeah, it's quick. It's a lot quicker. So copper media safety, cables must be connected correctly, equipment must be grounded, separation of data and electrical power must comply with safety codes, installations must be inspected for damage. Basically, the thing to know about copper is that we still use it because it's so much cheaper than anything else, but it's susceptible to interference. And copper, things happen to wire. It's just the way it is. I helped them, I guess it's been about 4 years ago, diagnose a weird problem out at Louisiana Technical College here. They had a run that was a little bit too long, but had worked for a long time, and it quit working. And we couldn't figure out what was going on. Finally, we got some tools and diagnosed the cable and found a break in it. And after digging, found that a rat had chewed a hole in one of the cables, just one, so it was loose, but it would connect if it was a little bit warm enough that that wire would expand just a tiny bit. It would make a connection. So weird things like that happen. All right, so here they're talking again about EMI. EMI is the electromagnetic interference I was telling you about. So there are different categories of cabling with UTP and with STP. And the category in almost all cases refers to where the twist is in that cable. Category 3 is kind of old. You still see it in some phone installations. Category 3 was approved in networks for up to 10 megabit connections. So in the old days, that was fine. 10 meg internet was faster than most internet, most schools or anything else had. Nowadays, what you see more of is 5, 5E, and 6. And it refers to the number of twists in there. And Category 7, SCTP, I'm looking at that and I see the shielding on it, and I'll tell you, I've never even seen Category 7 cable. I would assume just from reading it, the reason for it is to try to push those faster speeds. Here are the different connectors on the end. This is what an RJ45 socket looks like. If you look at the end of it, you've got little places that you push the wire down in. This is what's in the wall, like that plug up there in the front. In the back of it, the wires go into these little places, and you get a thing called a punch down tool that pops the wire down into it so that you can plug your cable in. Now this is the wiring standard. This is the 568A and B. There is no one answer to what a company should use. But what is extremely important is that a company pick one of these two and stay with it. It will be a nightmare if part of your building is wired A and part of it B. Really, it seems like more places are using B, but it's not required. A building can be A. And in the old days, you would make what's called a crossover cable. And a crossover cable is AN on one side and B on the other. And what that crossover cable was used for was to connect two switches together. Well, now almost all switches are what are called auto sensing. If you plug in a cable to another switch, they'll sense that it's another switch, and the switch itself will do the crossover so your cable doesn't have to. I think the Cisco test will have the colors of these wires on it, but I'll tell y'all the Net Plus test does. So make sure you know it for your Net Plus. And it's sad because you're just going to memorize it for that test and then forget it. I don't know these. It's something that if I need, I'm going to pull up on the internet real quick because information is so readily available. I know people that actually do this more often. I've got friends that actually do wiring for a living. They'll keep it on a little card in their wallet, so if they need to wire something, they'll pull it out and look at it. Cable is something that Cisco has that's a proprietary cable. And on a rollover, 1 through 8 are wired 8 through 1 on the other end. And we'll talk about rollovers later. So here they've got a device showed to test a cable. And there are different types of testers. Some of the more expensive ones will tell you the length of the cable. They'll give you a wire map showing what pair of wires on one end is what pair on the other. And they'll tell you how much signal is being lost across the wire. Different ones, some of them have a little device that you plug into the other end of a long wire that will send the signal back to tell you which wires are what. Some have 2 plugs on them. You have to plug both ends of the wire into it. And then another type of device that be aware of that you use a lot is called a fox and hound, or a signal generator. And what that does, you put that on a wire, and then you can go looking in your pile of wires that you should have documented but didn't. When you touch the wire that the fox and hound is plugged into, it makes a sound. So that's so you can determine what wire is what. Whoever in charge of a network setting it up from the ground up, my biggest piece of advice is document, document, document. It will save you time in the future when you have to go back and try to figure out what something is. I attempted to document some of the stuff over at LSUS, and it was just a nightmare. We had wires that we had no idea what they went to, but it was running, so we didn't want to take them down and fix it. So here's an example of some fiber. There are 4 standards being used in fiber right now. An enterprise network, a fiber to the home, which I wish we could get here. That's stuff like Fios and True UVerse. Long haul networks, that's where phone connections are made with the telecom phone companies and ISPs, where they run fiber very long distances. And then submarine networks are specific types of connections that are used for the transoceanic cables. So most of those are waterproof and buried. Here's an example of a typical piece of fiber. You've got a jacket, some strengthening, a buffer, cladding, and then the actual glass that transmits on and receives on is the core in the middle. This strengthening material is important because fiber can't be bent too much into an angle. If you bend a piece of fiber too much, you can actually break the glass in the middle, and it'll quit working. Here they're showing the differences in single and multi-mode. Single uses a smaller core and uses a more focused light source. A single mode fiber is only a laser. Only a laser can do it. But you can run single mode a long ways. Multi-mode is cheaper because you don't need as fine of a laser. You can actually use an LED for multi-mode. But because that signal is not as fine, it bounces around in the cable. You can't go as far with it. Here are 4 of the major types of fiber connectors. ST, SC, LC, and then a duplex multimode connector. I don't think the Cisco test asks it, but this is another thing you can throw on your list for Net Plus. In the Net Plus test, they're going to give you, or at least on mine they did, everybody gets a different one. I had a picture of a fiber connection and I had to identify it. And luckily it was an SC, which I knew. Here they're showing a fiber tester. This is not that different from a regular tester, except fiber cable testers are still very, very expensive. So here is kind of their rundown on fiber versus copper. And you'll see that copper media, 10 megs to 10 gigs is about it. Fiber, they say 10 to 100, but in truth, it's far beyond that. I read an article, I guess it's been a couple of years ago now, that said that we keep increasing our speed on fiber optic, and they don't believe that we've even reached 1/10 of the percent of a potential of what can actually be sent over fiber optic. Right now, we tend to still send things with just one laser. Well, imagine the amount of bandwidth when they get that to where they can do a couple of different color lasers in a single wire, or things like that. So it's going to continue to go more and more. Distance, your copper media is relatively short. Fiber optic is relatively high. You can run it a long ways. EMI is low on copper media, but it exists, and electrical hazards are low but exist. Fiber is pretty much completely immune to these. If we were running fiber in here, I could run it all up and down these lights. It wouldn't matter. Thing about cost and installation, it's pretty easy to do things with copper. It's pretty difficult with fiber. If you break a fiber cable, you can't just put ends on it and crimp it back together. You actually have to get a kit and a microscope and piece the fibers back together. It's very, very difficult to do. So wireless has some areas of concern, including coverage, interference, and security. Some of the common types of wireless media, Wi-Fi, know the different ones here, the 802.11, ABG, and N. ABG and N are the most common. AC is relatively new, but it's upcoming, and AD I didn't even know about until a few days ago. AD is faster than what most people have for wired networks. But again, they're trying to come up with faster and faster wireless to keep up with wired connections. Bluetooth 802.15 supports speeds of up to 3 megabits. Bluetooth is becoming more and more prevalent. I know that I don't think they're far away from passing a hands-free law in Louisiana. There's already one out here on the base. You can't use your phone unless it's hands-free. I kind of think it's not going to be long before that's sort of a statewide thing. But more and more cars and computers and things have Bluetooth because of those laws. And then WiMAX is the 802.16 standard, and this is something they're using to try to get internet out to what they call the last mile. And the last mile is basically those few people that still live in rural areas that don't have access to high-speed internet. And there are some, believe it or not, there are still some places where you can't get anything but like satellite internet. So WiMAX is an answer to that. An example of their one of their wireless routers, that's an EA6500. And here are the speeds and the frequencies on the different Wi-Fi standards. I don't like memorizing things, but this is one of those slides I'm going to tell you kind of better memorize. I don't know if Cisco will ask you questions on the speeds, but I tell you Net Plus will. ABG and N especially, because those are by far the common ones. And one thing that's interesting to note is most of these are backwards compatible. Notice the AD standard is backwards compatible with B, G, N, and AC. So here, data link, we're talking about things that are happening at the second layer, the lower layer, one of the lower layers of our network. Data link is broken into two sublayers called LLC and MAC, and that stands for Logical Link Control and Media Access Control. And notice the MAC sublayer, does that look familiar to y'all? That's where a MAC address comes from. That's where the term MAC address actually comes from. So here we're just giving another example. Data link layer protocols govern how to format a frame for use on different media. Different protocols may be in use for different media. At each hop along the path, an intermediary device accepts frames from one medium, decapsulates the frame, and then forwards it in a new frame. The headers for each frame are formatted for the specific medium it will cross. What we're trying to point out here is that what that means is upper layers don't have to worry about how their data is transmitted. The lower layers take care of that for you. Here they did a good example. They've got a picture of a satellite. Well, when you send data through a satellite, it tends to take several frames and make what are called jumbo frames. And those jumbo frames have a lot more data in it than is typically in a packet that's on a regular network. So it takes the data and it pulls all that frame data off of it for MAC addressing and puts it in a different type of format that's specifically for the satellite. And that'll send it up and pull it back down, and then the router at the other end is going to take that and take it back apart and put it back into a format that can be sent out on wire or whatever kind of network it is. The beauty of the layered approach to networking, and the reason that it's so popular and TCP/IP has become so popular, is upper layers don't care about what lower layers do as long as they do them. Think about the command ping. Have y'all used ping before, to see if a server's up? When you ping something, it may go through several different transmissions, and it may get converted, but it's ultimately the same way on the other end. Ping doesn't care what happens between here and there. It just looks to see if it's up or not. And here they're showing some more providing access to media. We've got a serial connection between a couple of routers. Serial connections typically have that little Z in the middle. As y'all start playing with Packet Tracer, you'll notice that. So here we're formatting data for transmitting it out on the internet or any kind of network. We've got the header that's got information in it, our data, and then they call it a trailer, but I tend to call this a footer a lot. Old Cisco called it a footer. And in it, you see there's just a frame stop bit and error detection. So here we're showing how we actually created the frame. And again, more of these standards on how things are transmitted. 802.3 is probably the most common one on this list. 802.11 is probably shortly behind that. Ethernet and then wireless are the big ones. 802.5 token ring is one that was popular about 15 or 20 years ago when IBM was in its heyday. IBM had a token ring network that was designed to directly compete with Ethernet, but Ethernet won out in the end. You have some others that are standards with other companies, so you can kind of take a look at the list. So there are rules that have to be followed on how to share media. And the reason for that is that we're all connected to one network. This part gets kind of hard to understand because most people only work with switches these days. But the way a network is actually designed, in the old days you had what was called a hub. And a hub was basically like a party line. All these computers, if they were on a hub, when one transmitted data, no one else could transmit data at that moment. The line was full, if you will. Computers just did that very fast, so it didn't matter that they were all talking in pieces, as long as they weren't talking at the same time. And that's where some of these rules came in that we talk about. Here they want to show physical and logical topology. And I went into that in Chapter 1. I'm not going to go over it again. They're showing a layout here Physically, we've got a layout of a star because I've got a hub or a switch that everything's connected to. But logically, those are broken down on a bus network. Are y'all all pretty clear on the differences in physical and logical? And then this straight out of 101, the different type of topologies. A point-to-point where one connects to one other one. A hub and spoke where different machines connect to one central location, or routers connect to one central router. And then a full mesh where everyone is connected to everyone around it. What is way more common that they didn't show here is a partial mesh, where everyone may be connected to one or two other people, but almost everyone is not connected to everyone. Full mesh is by far the best way to go and the most redundant, but it's also the most expensive. Looking at just their picture here, you see that every router in this diagram has to have at least 5 connections to hook to every other router. Point limited to 2 nodes. I've got a node on one end connecting through the network to a node on the other end. Typically, the point-to-point may go through all kinds of other connections, but it's still a single point. I've got a source node and a destination node and a frame that needs to be transmitted, and if I'm making a logical point-to-point connection, I don't care what happens in the middle. My source and my destination do not care how many routers or what media it goes through to get there. Another important term is half and full duplex. And half duplex means you can send and receive, but not at the same time. Full duplex means you're able to send and receive at the same time. And that's how they started gaining speed on networks. Your first networks were 10 megabit half duplex. You had to send something and then you could receive, and then send and then could receive. Well, as soon as we started using more wires in that pair of wires, we could send and receive at the same time, and that sped up the network tremendously. So physically, looking at some of the layouts, a star is what you're going to see more often. That's where all the computers are connected together to a switch of some kind or a hub. Extended star, you have a couple of stars that are hooked together. Bus, that's your coaxial network. Your cable network at home is basically a bus network. And then a ring topology we didn't talk a lot about, but that's that token ring standard. And that's where all the computers are connected on a ring. Usually this ring was done with coaxial cable. Ring topology, the reason that it got to be popular at all, it was actually faster than Ethernet. And there was no chance of collision because on a token ring network, only the computer that has what's called the token can transmit at one time. So only one computer had the capability of transmitting at one time. Showing a couple of different ways to deal with shared media. Contention-based, I try to send when I'm ready. That's what Ethernet is based off of. When a computer has data, it just throws it out there and hopes nobody else is talking. Controlled is token ring. You can't send data until you have the token to be able to send. And those two standards are called CSMA CD and CSMA CA. It stands for Carrier Sense Multiple Access Collision Detection. And I can't speak today. The other one is collision avoidance. So what actually happens on a network when two computers communicate at one time? With switches, it's not a big deal because the switch deals with them talking at one time. But if it's an old network and it's a hub designed on the original standard, what those two computers would do is they would detect that they'd collided. And then each has a random number generator that goes off, and they wait the amount of time in that random number generator before they transmit again. The theory being that the chances of them getting the same random number is low, so one of them is going to get to transmit and one of them is not. Now, when we think about it, it sounds like that takes a lot of time, but remember, computers do this stuff very, very, very fast. So I'm breaking it down in a way that makes it seem like it takes forever, but for computers, this is just milliseconds of time. So here in multi-access, we got another example. If one needs to transmit, say A needs to transmit to E, it looks for transmissions. It doesn't see anything, so it sends its data. In controlled access, I have to wait for my turn. This is token ring is a good example there. Here they're going to show a little more about token ring. The frame goes all the way around the network. Each computer looks at it and says, is this frame for me? If the answer is yes, I'll read it. If the answer is no, I will pass it to the next person on the ring. That's why it's a ring. It keeps going all the way around until it gets to its destination. Here they're showing a little bit more about a frame. Greater effort is needed to ensure delivery with higher overhead or slower transmission rates. They say in a fragile environment, more controls are needed. I kind of like their little graphic here. They're showing rain. Rain messes with satellites in all kinds of ways. So you need a little bit more ways to make sure that the data gets there, and it gets there intact. And that's where that CRC check in the footer comes in. You can check your data. Basically, a CRC is a mathematical computation on the data. And your computer, when it sends the data, will compute a CRC and put it in there, put it in the packet. Then the other computer gets the data and computes it again, and the numbers should match. If they don't match, then it means something didn't go right. The data didn't quite get there the right way. Just showing what the header looks like. A header's got a start frame, the address, the type and length, then the data, the checksum, and finally at the very end, a stop frame. Here they're talking about the frame check sequence, which I already went into. So when data goes out on a network, what's interesting and important to know is that it may go through several types of layer 2 frames. In their example here, I've got a wireless computer that talks to a router that's going to send an 802.11 wireless frame, and then we've got two routers hooked up with PPP, which is point-to-point protocol. So they're going to have a PPP frame. Then I've got two routers over here using HDLC, which is just another type of connection. So they're going to have an HDLC frame. Then down here, just to make it more complicated, I've got a frame relay network. So I'm going to have frame relay frames. Finally, at the end, I've got a switch and a router hooked together, so I'm going to have an Ethernet frame. And then that Ethernet frame is finally going to get transmitted on to the actual computer I'm trying to send the data to. So what's important is to see that it went through several different types of frames, but the data still got there because of encapsulation. Here they're showing the actual sizes of some of these things. Frames have got a preamble. The preamble is used for synchronization. It's always 8 bytes. A destination address, which is going to be 6 bytes or a 48-bit MAC address. The source address, which is also going to be a 48-bit MAC address. A frame type, which will tell what type of data it is, or frame it is. Then the data itself, which for Ethernet can be between 46 and 1500 bytes. Then at the end, I'm going to have the frame check, and finally I'll have a stop frame over in the corner. So here in looking at the types of frames, this is a point-to-point frame. A flag is a signal that indicates the beginning or an end. The flag always consists of this binary sequence that they're given. The address is a single byte that contains the broadcast address. I could go into all of these reading them. I'll let you read them yourself. But you see, this is where we're starting to get bogged down in the absolute details that go along with Cisco. The wireless frame, and you see that this looks a lot like an Ethernet frame, except I've got some extra information on it. I've got a fragment number and a sequence number, and I've got some frame control numbers. What's interesting about this is that at the end of all of this, when I actually get to the data, I'm going to have an Ethernet frame inside of that data. And that is kind of a quick rundown of Chapter 4. The big thing in 4, we started getting into physical layer. Make sure you review the stuff on physical layer. Make sure you know the different types of wireless. I don't know how detailed the new Cisco exam is going to be about knowing the sizes of the different types of frames. I don't personally feel like it's that important, but as you're going through the chapter quizzes and, see if they ask a lot of questions on it. If they do, you can kind of rely that that's something you're going to need to know for the Cisco exam. Do y'all have any questions? This stuff is so riveting, right?